Okay, thanks for inviting me to come and speak about my favorite planet, Venus, which is actually the most Earth-like of the terrestrial planets. And it often gets called Earth's twin. Just to remind you, it's similar in size and bulk density. It at some point had a shallow ocean's worth of water, and perhaps most importantly, it's a relatively young surface. It's been geologically active, very active within the last billion years. It sometimes gets called the evil twin because of its greenhouse gas, which gives us this temperature that's hot enough to melt lead, and this dense atmosphere. And of course, it has no magnetic field. But the real question is, what about its tectonic style? Certainly, there's no evidence for terrestrial style plate tectonics, but we'll talk about that a bit. So I want to just give you a brief overview of what we know about the geology and the composition. I want to talk a bit about some recent data that's come from Venus Express that gives us some more information about the surface composition, and then talk about some of the inferences and maybe even myths about the interior. Okay, so some of the main features are these hotspot-like features, the long chasmata troughs with fractures, and these tessera plateaus, and I'll show you some examples. And just to remind you, this is sort of the data set that we have to work with, acquired some time ago now. The topography is on the scale of 10 to 20 kilometers. We have synthetic aperture radar on the order of 100 meters, and then gravity about to degree in order of 40 to 90. And then this new data from thermal emissivity. So there are about 10 hotspots, and these are some of the features that are actually pretty well agreed upon in terms of their origin. They have a broad topographic swell, volcanism, sometimes rifting, and a gravity signature that implies plumes at depths. So we have about 10 of these. We also have smaller scale features, corona, and there are about 500 of them globally. They may be upwelling, maybe downwelling. There's a variety of proposed models, but at least some of them are believed to be small-scale mantle upwelling. And basically Venus is a volcanic planet. About 80% of the surface is volcanic plains, and there's a huge number of volcanoes present. There are also these tessera plateaus, and these are highly deformed features, multiple directions of deformation, and they're thought to be perhaps analogous to terrestrial continents. And we'll talk a bit more about them. And then I just want to show you a little bit different perspective to show you some of the biggest rift systems. These are 8 to 10,000 kilometer long rifts. Globally there's tens of thousands of kilometers of rifts. But as you zoom in, this is a pargochasma here. It doesn't look exactly like terrestrial rifts for sure. One thing you'll notice are these corona, these quasi-circular features, deformation features with volcanism associated with them. And they are typically found along these rift systems, and vice versa. Most rifts have corona. So clearly there's somewhat different processes going on than just in terrestrial rifts. What do we know about the composition? Well, back in the 70s, the Soviets sent many landers to the surface, and a number of them had X-ray fluorescence and gamma ray spectrometers. So we know from that data, which of course had pretty big error bars for the time, but we know to first order that the composition is basaltic to alkaline basaltic. And you can see there's a number of different layers there. They could be aeolian, they could be from weathering horizons, but typically they're interpreted as platy basalt, just on the surface of lava flows. And this is sort of taken these 1970s TV images and reprocessed them with modern methods, and so this is what someone has inferred the surface looks like. Okay, so this is a plot of the topography in the same scale, and this is the type of information that's been used to infer that there is no interconnected series of plate boundaries on Venus, and it has a unimodal distribution of topography as opposed to a bimodal one. From the gravity, we have learned a number of things. The gravity and topography are very highly correlated, perhaps because there's very little erosion is probably one factor that contributes to that. The highland features have been divided into two types, the tessera plateaus and the hotspot regions, not only is their surface geology different, but we see that the highlands are isostatically compensated, sort of adding to the analogy that they could be continent-like, and the large volcanic rises are deeply compensated, thus and interpreted as having plumes underlying them. You can't derive elastic thickness over all of the planet. The resolution's not that great, but you get a variety of ranges from the places where you can infer elastic thickness. And similarly with seismology, the crustal thickness is not well constrained, but a 30-kilometer mean is a reasonable value, and you can certainly get a lot of variation on that. An interesting result from the analysis of the geotopography ratios for these hotspots is that data has been used to infer that there's no low viscosity zone, because the values are much higher than they would be for terrestrial hotspots, where the low viscosity zone decouples the deformation from the plume as it's imparted to the topography. So there's more coupling if there's no low viscosity zone, and that's what's been inferred from these geotopography ratios for Venus. And from the Lovener, we infer that there's likely a liquid core. Okay, so to talk a bit about the new data that we have for Venus, this is derived thermal emissivity around 1 micron from these papers by Mueller and Halbert. And the emissivity is retrieved from the surface brightness, taking into account instrument and atmospheric scattering effects. And two very interesting results have come out of that data. One is that low emissivity is correlated with tessera terrain and high emissivity with some volcanic flows. And you probably can't see it very well in here, but there are some contours in here basically of the number of observations. And so basically on this side, the observations are, there have been more repeat observations and the data has less uncertainty. So the best observations are sort of in this area. And there's only one tessera plateau in the southern highlands, southern hemisphere rather, and that's Alpha Regio, which shows up as having a low emissivity anomaly. Some of these other ones are not really to be terribly well believed. And similarly, the three hotspots that are in southern highlands, Dione, Themis, and Imdir, all have high emissivity anomalies. So this 1 micron band corresponds to the iron oxide absorption band. And so a low emissivity means low iron content, and one can infer perhaps that means high silica. So that's what it was seen at Alpha Regio, and people have made the leap, and this has been proposed even before this data. But if you have on Earth, the continental crust forms in the presence of water, and so the hypothesis that has been put forward is that you have low emissivity, perhaps high silica, and perhaps evidence of past water. Now, I should also say that the tessera are everywhere stratigraphically the oldest material, and so they've been proposed to record the past history of tectonics on Venus. Now, one reason that this result has not received more attention is that it's complicated by the fact that the Magellan altimetry has a very large uncertainty in these rough, deformed areas, tessera. And so, in fact, the uncertainty in altimetry is large enough to possibly account for that anomaly. So people have been a bit reluctant to push that interpretation too far. So this just shows on the top the altimetry and radar, and on the bottom the emissivity for these three areas that have been in the past proposed to be hotspots. You can see they all have a number of high emissivity anomalies. And in this one region, Themis Regio, there's a number of corona and volcanoes that all have high emissivity anomalies. So in these areas, the interpretation has been that the high emissivity could be either compositional differences, high Mg, titanium, or iron. Although if that's the reason for these anomalies, they would still weather under the Venus atmosphere. So the preferred interpretation is that the background average emissivity are weathered basalts, and that the high emissivity anomalies indicate unweathered basalt. And that's based on both laboratory experiments and thermodynamics that predict these type of minerals for weathering products for basalt, and they all have lower emissivity relative to an unweathered basalt. Even though this is thermal emissivity, we do not believe it's indicating that these are active flows because the data has been acquired and averaged over a year and a half, and flows simply don't remain hot that long. And you can estimate the volume of this volcanism to try to say, using resurfacing rates, how old they are, but that's not a very strong constraint. You can get a range of ages. And certainly the laboratory experiments indicate that material tends to weather very rapidly under the corrosive Venus atmosphere. So possibly they could be quite recent. So just some additional evidence that might suggest that this is a reasonable interpretation. You know, as I said, all of these areas have previously been interpreted as having mantle plumes at depth. And the anomalies correlate with volcanic flows, and those are the stratigraphically youngest flows in this area. Additionally, there's been data from Venus Express indicating that the SO2 has increased over the last decade, and one possible interpretation is that that's due to recent volcanic outgassing. So what does that mean for the interior? Okay, so it's very conveniently, these are all hotspot regions that have this type of high emissivity anomaly. And I will note that the resolution is like 100 kilometers, so it's certainly possible that there are other volcanic regions that haven't been well resolved. But if we take this interpretation that the volcanism is primarily found in hotspots, and it could imply that the plains volcanism is no longer active. It's interesting in that we need to have a hot boundary layer at the core mantle boundary, and without a magnetic field, the question is enough heat being lost from the core mantle boundary to produce these plumes? And a number of studies have looked at that recently, trying to look at the balance between heat loss from the core, the amount of internal heating, and the fact that Venus is believed to be in a stagnant lid regime. So, depending on your amount of internal heating and so forth, you can produce plumes, but it does provide some interesting constraints on the amount of internal heating. Okay, so another point is that this Themis regio shows multiple volcanic sites. And one way to interpret that is that there are two scales of plumes being active. And certainly on the Earth, there's still debate about how many plumes are active and what volcanism actually corresponds to a plume and so forth. But one model that I've favored is this one that's put forward by Cordio, and he takes data from a variety of sources and suggests that there are plumes that come all the way from the core mantle boundary, like Hawaii, and other places like the Pacific superswell that perhaps cores get hung up at the upper mantle, lower mantle boundary and generate smaller plumes. And of course, there are other sources of volcanism as well. And one reason I like this model is that it seems to be relevant to Venus, and this is obviously not to scale, but we do see these regions where there are multiple centers of volcanism, as well as areas where there are more a small number of volcanoes. And so this kind of model, which we had suggested previously, applies to Venus. Seems to be consistent with what we're seeing in terms of these centers for multiple volcanoes being active at Themis currently, and only one or two at these other areas, Imdir and Dione. Okay, so switching gears, I want to talk about the geologic history and the impact cratering record. That's obviously an important constraint we have on understanding the geologic processes. And as I said, Venus has a relatively young surface age. It has about 1,000 impacts, and one thing that was surprising initially is that not very many are modified. Only a relatively small percentage have clear evidence for tectonism or volcanism. And so that led initially to this catastrophic resurfacing hypothesis. If you look at the distribution of craters, they cannot be distinguished from a random distribution statistically. And as I said, very few are modified. Most look like this pristine-looking crater rather than this more flooded crater. Geodynamicists leapt upon this idea because it's very intriguing to try to model a very big pulse of volcanism followed by a decrease in the amount of volcanism. And in fact, perhaps this might have even led people to explore the possibility of having episodic convective models. Climate modelers also love this because if you have a huge pulse of outgassing from volcanism that can also produce very big climatic changes, perhaps up to 1,000 degrees. So, but people have continued to explore this idea and look at different types of resurfacing models. So this is the catastrophic one, where the red is the volcanism, and you cover the surface of the planet completely in one fell swoop, and then you add the impacts. This is an equilibrium model where the volcanism is at a constant rate and the craters are at a constant rate. And then people have also looked at regional equilibrium, where you have volcanism in one area and then another and then another. And basically, the models that have been done more recently tend to favor the equilibrium or regional equilibrium resurfacing models. And some other studies that tend to support this idea are one by Herrick and Rump, where they used a subset of craters for which there's stereo data, so higher resolution topography. And they showed that the dark floored craters, which actually make up about 80% of the craters, have evidence for being flooded, at least in those subset of craters they were able to study. So if this is the correct interpretation, then the surface could in fact be as young as 150 million years, and would certainly require ongoing volcanism. Other models have looked at the erosion of halos and parabolas. These are extended ejecta, very fine-grained material that's carried by the winds downstream by up to 1,000 or 2,000 kilometers. And if you also incorporate statistical modeling that looks at how those features have been eroded over time, that prefers these equilibrium models as well. So, I would say within the community, the very small community of people that still study Venus, there's really been a shift to being more weight towards the regional equilibrium resurfacing model. So there's no geologic requirement for an episodic plate tectonic model. But on the other hand, we don't know what happened in the 3.5 billion years before the current surface was laid down. So it's certainly within the realm of possibility. Now I want to talk about the possibility of plate tectonic mechanisms on Venus. And certainly right after the Magellan mission acquired data, there was a number of papers that were put forward proposing that subduction occurs on Venus. And this is data at the same scale for Earth and Venus. And you can see there's a strong resemblance between these ocean-ocean subduction zones and some features on Venus. And if you model the topographic profiles across here, you get similar elastic thicknesses, similar bending moments. This is another example from Artemis Corona, where you have a large trench. This is the Venusian one, and again, you can get similar results in terms of the elastic thickness. This idea of having subduction on Venus, I think, was somewhat discounted for a few different reasons. One is that these arcs that resemble trenches always found in conjunction with these corona, these semicircular features, most of which have been interpreted as evidence of mantle upwelling. But you can see that this is the trench. It's 2 kilometers deep, and there's a lot of deformation features across here, similar to what has been seen for terrestrial subduction zones. But this has been interpreted as a mantle upwelling. And people tried to come up with ways that you could link these processes. This is one in which volcanic loading caused the lithosphere to founder. Here, this model took into account the fact that it's along this trench, and perhaps that the lithosphere was initially weakened at the trench, and that could allow it to be broken and subducted. But there were some other issues raised also, that some fractures appeared to continue across the subduction zone. But really, I think it was this idea that these are upwelling areas as opposed to subduction zones that kind of kept this idea from becoming more popular. Now, subsequently, there have been studies for terrestrial regions where they've tried to link upwelling and the formation of subduction zones. So this is one study from Ueda, and showing that you can get weakening of the lithosphere due to a plume, and that could lead to subduction, pretty much like that, analogously to that cartoon from 1992, really. But one thing that I've found persuasive in terms of trying to understand how these features might be formed, linking plumes and subduction, are these experiments conducted by Devay and colleagues. And this is a tank model in which their group has been trying to model plate tectonic processes very accurately for some time. And they do that using polymers and colloidal solutions to get a good representation of the rheology of a lid with elastic, viscous, and plastic deformation and over convecting region. Because, of course, it's this type of process with these range of rheologies and the viscous deformation in the lithosphere, which is hard to fully model in numerical experiments. So what you get is, as the solution evaporates, you get a brittle layer here, a more viscous lid, and convecting mantle. And one nice feature of these models is that the drying causes micro cracks to form throughout the upper lid, which in fact mimics what's seen in the lithosphere. So you get features that occur on a range of scales from microns to meters, and these processes mimic the contractional cracks that you see in brittle layers, folding, and then the convection processes in the interior. And it's great because it's in 3D and allows you to actually compare these features to what we see on the surface of planets. So this is a model of a laboratory experiment showing plume that's come from the base where it's heated and initiating subduction on one side of this plume. So looking at the surface, you see an arcuate region of folding on one side and a slightly different arc on the other side. And so basically the deformation above the plume produces these ridges. And looking at them in 3D, this is sort of a cartoon of the process that happens. The plume stress causes delamination, as has been predicted in some numerical models. What the numerical models don't show is the fine-scale deformation of the surface. And here, this is in the lab, there's a ridge that forms, and as that progresses, the lithosphere can actually break and be pulled down by its own weight as well as that of the overriding plate. And some experiments, this subducting region can either neck and drop off or continue to develop into a more widespread subduction event. So I like these experiments because they link very, very closely the observations of what we see above plumes and these subduction characteristics. So some further implications of this is that in the laboratory experiments, Anne and colleagues predict both a range of behaviors: stagnant, sluggish, and plate tectonic regimes. Those regimes can transition from one to another. And what's interesting in particular is that the strength increases from sluggish to plate tectonic and stagnant. And it's this sluggish area that we see that most mimics features seen on Venus, including other features such as shear zones. Okay, so does Venus have plate tectonics? I've showed you some evidence that it may have subduction in a number of areas. That doesn't mean it has plate tectonics. But the question is, if it doesn't have terrestrial-style plate tectonics with an interconnected set of plates, why is that? And for a long time, people have basically said that it's most likely due to a lack of water. If it doesn't have a low viscosity zone, that makes it harder to perform plate tectonics. If the crust is very dry and thus very strong, that makes it hard to break the plates. But do we really know very much about what the interior is like in terms of its volatile content? I think this idea that Venus is completely dried out has become a bit more difficult to accept as we've learned more about how planets form and the evidence for volatiles throughout the solar system. Planets are thought to form very wet, and yes, there are processes that can desiccate them, such as large impacts or some magma ocean processes, but for the most part, it's pretty hard to dry out a planet. And certainly as we get more data for Mercury, for even the moon, we see more evidence of water and volatiles throughout the solar system, and even learning more about how a large amount of water can be contained in the deep Earth. So where did this idea come from that Venus is dry? Okay, so the lack of a low viscosity zone, and I must say that's only comes from data for these hotspot regions, has been suggested that it as an indication that it's dry. Another idea that people have suggested could indicate that it's dry is that there are very high plateaus, 4 kilometers, even mountains up to above 10 kilometers, and under Venus temperatures, those things want to relax very, very rapidly, unless the interior is dry. But in fact, we have no actual constraints on how old those features are. Because of a very small number of craters, we can't really say any one feature is older than another. You can't use impact craters to get a date of an individual feature. Of course, the atmosphere is very dry, but that doesn't necessarily tell us a lot about the interior. I mentioned that there's sulfur content has continued to increase over the last decade or so, and it's possible that outgassing is still continuing, both water and sulfur. One interesting measurement that was made some time ago, which suggested Venus, in fact, is still wet, is the argon isotopes. And if you take a reasonable assumption about the amount of potassium in the interior, it suggests that Venus is only about 25% outgassed, as opposed to the Earth, which is about 50% outgassed, based on that type of analysis. So a relatively new idea that I wanted to bring up is the idea that temperature could be preventing plate tectonics in Venus. And there have been a series of papers by Berkovici and Smrekar looking at damage theory of how lithosphere deforms, and they suggest that the ability of the hotter lithosphere to heal faults on Venus could be what's preventing large-scale faults, through-going faults and lithospheric plates from actually developing. They predict that you could get subduction, but that it wouldn't progress into a larger fault system as they predict for the Earth. And there are also studies of Venus in terms of the effect of high temperature on convection, which also suggests that that could be helping suppress plate tectonics. So this is a sort of a summary of what we know about Venus at the moment in terms of its tectonics and dynamics. We know that it doesn't have terrestrial-style plate tectonics, but I think there's a good case to be made for subduction, perhaps driven initiated by plumes. There is no geologic requirement. There's no requirement there be catastrophic resurfacing, but of course we only have the record for the last billion years. And I think there's good evidence that there's no low viscosity zone under hotspot plumes, but that's perhaps not surprising if you have upwelling material over a long time, that it would be dried out in that particular area. We really don't know if there's a low viscosity zone in any other part of Venus. Certainly this new result that there's very likely active and geologic timescales, volcanism at mantle plumes, is interesting, as well as the idea that there's probably both large-scale and small-scale plumes. And of course, we still no magnetic field, so that's definitely telling us something about the heat loss over time. As we learn more about processes on the Earth and try to extrapolate that to Earth, we can also take those lessons and try to extend them to exoplanets. And perhaps what we may be learning in terms of a new parameter that's important is the temperature of the surface. So that's my summary, and then I'll take my last minute to shamelessly tell you about this conference that's coming up in Pasadena in May. You can talk to me, or Laurent Montisi is another organizer for this conference, and we're trying to bring people together to talk more about tectonics and geodynamics of Venus, Earth, and exoplanets. Okay, thank you.